Have you ever looked up at the night sky and wondered how a tiny metal box floating thousands of miles above Earth can beam your favorite show straight to your phone? That is the magic of satellites, and today we are diving deep into the science that makes it all possible. Satellites are not just chunks of technology orbiting our planet. They are masterpieces of physics, engineering, and human ambition. From predicting weather to guiding ships across oceans, these silent sentinels shape modern life in ways most people never notice. By the end of this video, you will understand exactly how they work, why they stay in orbit, and what the future holds for space technology. Let us start at the beginning. The idea of satellites dates back to 1945, when a science fiction writer named Arthur C. Clarke published a paper suggesting that spacecraft in a specific orbit could relay radio signals around the globe. Most dismissed it as fantasy. Yet just 12 years later, on October 4, 1957, the Soviet Union launched Sputnik 1. This polished metal sphere, no larger than a beach ball, weighed 83 kilograms and emitted a simple beep that echoed across radio receivers worldwide. That beep marked the birth of the space age. Sputnik 1 orbited Earth every 96 minutes at a speed of 28,000 kilometers per hour. How does something move that fast without flying off into space? The answer lies in orbital mechanics. Satellites do not hover, they fall. Gravity pulls them toward Earth, but their forward velocity is so great that they keep missing the planet. This balance between gravitational pull and tangential speed creates a stable orbit. Think of swinging a ball on a string. The string is gravity, and the swing is velocity. Early satellites were basic. Sputnik carried a thermometer and a radio transmitter powered by batteries that lasted 21 days. But the launch proved two critical concepts. First, humans could place objects in orbit. Second, rockets could achieve escape velocity. These breakthroughs ignited the Cold War space race and accelerated satellite development. By 1960, the United States launched Ecto-1, a giant reflective balloon that bounced radio signals back to Earth. 2 years later, Telstar transmitted the first live television images across the Atlantic. These passive satellites gave way to active ones with solar panels, onboard computers, and transponders that amplify signals. Modern satellites pack more processing power than the computers that landed humans on the moon. Orbit types matter. Low Earth orbit, or LEO, sits between 160 and 2,000 kilometers above the surface. Satellites here zip around Earth in 90 minutes and provide high-resolution imaging or internet with low latency. The International Space Station lives in LEO, medium Earth orbit, or MEOW, ranges from 2,000 to 35,000 kilometers, and hosts navigation systems like GPS, geostationary orbit, or GEO-LOX satellites 35,786 kilometers above the equator. They match Earth rotation and appear stationary from the ground, perfect for television broadcasts and weather monitoring. Staying in orbit requires precision. Atmospheric drag slows LEO satellites, so they carry thrusters to boost altitude. Solar panels generate electricity, but radiation in space degrades them over time. Antennas must point accurately within fractions of a degree. Thermal control systems prevent electronics from freezing on the dark side or frying in sunlight. Every component is engineered for a hostile environment where temperatures swing hundreds of degrees in minutes. Communication satellites dominate the industry. A signal travels from a ground station to the satellite, then down to your receiver. This uplink and downlink use microwave frequencies because they penetrate clouds and rain. The satellite transponder receives, amplifies, and retransmits the signal on a different frequency to avoid interference. Bandwidth is split into channels, each carrying hundreds of television stations or thousands of phone calls. GPS deserves its own chapter. 24 satellites in MEOW broadcast time signals from atomic clocks accurate to billionths of a second. Your phone receives signals from at least 4 satellites and calculates distance based on how long the signals took to arrive. Trilateration pinpoints your location within meters. The system also corrects for atmospheric delays and satellite clock drift. Without GPS, ride-sharing apps, precision farming, and drone delivery would collapse. Earth observation satellites revolutionize science. Instruments measure infrared to detect heat, radar to penetrate clouds, and spectrometers to identify minerals. They track deforestation, monitor ice caps, and predict hurricanes days in advance. During wildfires, Thermal imaging guides firefighters to hotspots. Climate models rely on decades of satellite data showing rising sea levels and shrinking glaciers. Military satellites provide secure communication, missile warning, and reconnaissance. Some resolve objects smaller than a license plate from space. Electronic intelligence satellites intercept radio transmissions. Infrared sensors detect missile launches by their heat plumes within seconds. These systems maintain global deterrence but raise ethical questions about surveillance. The satellite boom brought challenges. Space debris now includes millions of fragments traveling faster than bullets. A fleck of paint can puncture a solar panel. The Kessler syndrome predicts a cascade where collisions create more debris, rendering orbits unusable. Companies now design satellites to deorbit within 25 years and use maneuvers to avoid junk. Innovation never stops. Starlink deploys thousands of small satellites in LEO to deliver broadband worldwide. Each weighs about 260 kilograms and lasts 5 years before burning up on re-entry. CubeSats, no larger than a shoebox, enable universities and startups to launch experiments for under $100,000. Reusable rockets slashed costs from $10,000 per kilogram to under $1,000. Future satellites will harness artificial intelligence. Onboard processors will analyze images in real time, reducing data sent to Earth. Optical lasers promise gigabit speeds between satellites, bypassing radio congestion. Quantum communication satellites could enable unhackable networks. Swarms of microsatellites might repair larger ones or assemble structures in space. Satellites shaped culture too. Live global broadcasts united humanity during the moon landing and the Olympics. Weather forecasts became household staples. Farmers optimize crops with satellite soil data. Disaster response teams coordinate relief using real-time maps. Even dating apps rely on GPS, yet few pause to appreciate the invisible infrastructure overhead. Here is a fun fact. The fastest satellite ever, X-37B, orbits at over 30,000 kilometers per hour and remains classified. Another surprise, Voyager 1, launched in 1977, is now a satellite of the Sun, over 24 billion kilometers away, still transmitting faint signals. One more. A satellite named Miyake tried to become the brightest star by unfurling a giant reflector, but it failed and now tumbles silently. Satellites prove human ingenuity can conquer physics. They connect continents, safeguard nations, and expand knowledge. Next time you check the weather or navigate a new city, remember the science silently circling above. If this video sparked your curiosity, hit the like button and subscribe to Objectified for more deep dives into the objects that define our world. Drop a comment with your favorite satellite use case. We read every one. Turn on notifications so you never miss an upload. Thank you for watching. Keep looking up because the sky is full of wonders built by science.